If you do not understand everything in this lecture, don't panic. We'll go through all these things in detail in the coming classes. As you saw in the last lecture, we discussed few introductory examples to understand limits. Now let's formalize whatever we studied to more formal way we call theorems. I will tell you some theorems, in this case without proofs. The proofs are very trivial and you can find them on internet, so let's just skip them for now. So theorem 1. Basically these theorems are going to simplify our tasks, that's why it's important for us to learn about them. So theorem 1. Let me change the color. Yeah, that's cool. Theorem 1. Let f and g be two functions such that both limit x tending to a fx and limit x tending to a gx exists. The limit exists. Then there are a few things if these conditions are met. First is limit of sum of two functions is sum of the limit of functions. What do we mean by that? Say limit x tending to a in bracket fx plus gx, it is equal to individual limits of fx plus individual limit of gx and just add them. Secondly, subtraction. Limit of difference of two functions is difference of limits of functions. That is, limit x tending to a fx minus gx is similarly equal to limit x tending to a fx minus limit x tending to a gx. Thirdly, we have multiplication rule. Limit of product of two functions is product of the limits of functions. That is, limit x tending to a fx times gx is equal to limit x tending to a fx dot limit x tending to a gx. So basically product of individual limits. The third one is going to be very important for us while we solve problems. Fourth one is division. Limit of quotient of two functions is quotient of the limits of functions whenever denominator is non-zero. That is, limit x tending to a fx by gx is equal to individual limit x tending to a fx divided by limit x tending to a gx. Now there is a special case of the third one. Let's say the gx is constant. In this case, what is going to happen is limit x tending to a constant time fx is equal to constant comes outside, it is not affected by the limit, and limit x tending to a fx. So constant times limit x tending to a fx, as you can see on your screens. If you didn't get any of these, don't panic. I'm going to show you some examples of what they exactly mean. Okay, so let's go through some examples. We can take fx and gx to be simple functions for now. Let's take fx is equal to x square and gx is equal to cos x. And first part of the theorem, if fx plus gx limit x tending to 0, so we break the individual limits to x square and cos x. When x tending to 0, x square tends to 0 and cos x tends to 1, so 0 plus 1 becomes 1. Similarly, subtraction. Let's say fx is equal to x square and take gx is equal to say sin x. So limit x tending to 0 fx minus gx. In this case, limit x tending to 0 x square minus sin x. So x tending to 0, x square becomes 0, it goes towards 0, and sin x goes towards 1. So 0 minus 1 is 0. 0 minus 0 is 0. C part. Fx is equal to x square, gx is equal to cos x. So limit x tending to 0 x square times limit x tending to 0 cos x. So x square becomes 0 and cos x tends to 1 as x goes to 0. So 0 times 1 becomes 0. And lastly, fx is equal to sin x, gx is equal to cos x, and say limit x tending to 0 fx by gx. So individual limits, and sin x goes to 0, cos x goes to 1, we get 0. Also, sin x by cos x is tan x. So we know that tan goes towards 0 as x goes to 0. So we can verify these this way as well. So it's correct. And lastly, the simple constant identity. If gx is a constant, then it simply comes outside the limit and rest remains as it is. So limit x tending to 0 cos x 3 times 1 is equal to 3. So this was all for this lecture. In the coming lectures, we will discuss more theorems, more identities, and we will be solving pretty more interesting problems in the coming lectures. So stay tuned.